Hello, good morning.
Good morning, ma'am.
How are you?
I'm fine, ma'am. What about you?
I am fine. Okay. Hello, Amelia.
Hello, ma'am. Good morning.
Good morning. Hello, Abira.
Good morning, ma'am.
Hello, Anam.
Good morning, ma'am.
Hello, Hamza.
Good morning, ma'am.
Good morning. अच्छा और कौन आया हुआ है माइजा हेलो माइजा
Hello, ma'am.
Assalamualaikum, ma'am.
वालेकुम सलाम हेलो फरीद
Good morning, ma'am.
गुड मॉर्निंग हेलो जरीश
Hello, ma'am. Hello, ma'am. Good morning, ma'am.
गुड मॉर्निंग हेलो हारिस हारिस Okay, so let's start. Let's start with a recap of what we did last time. So who would like to start? Yes. कौन बताएगा? Yes. Hello.
Hello, good morning, ma'am.
So who would like to start? I told you to prepare yourself, right? This was your homework. So please, or I call you out by your name, okay? Either you volunteer or I call you out. Okay. Abira, what did we study last time? Yes, Abira. Amelia.
Ma'am, we studied oscillations, oscillatory motion, which is back and forth motion.
Amelia, बेटा आहिस्ता आहिस्ता बोलो ताकि मैं साथ साथ लिखती हूँ, ठीक है?
Yes, ma'am.
Okay, so we studied oscillations, ठीक है? आगे?
Oscillatory motion, which is back and forth motion.
This is back and forth motion or to and fro motion, like we described a pendulum, for example. This is or even you can consider this like a child on a swing. You know, such a motion is known as a oscillatory motion. Yes.
And we studied different examples of it.
Okay, that's good, Amelia. Let's go to the next person. Okay, Anam. What would you like to add?
Ma'am, I was not in the last class.
Beta, even if you're not in the class, you still have access to all what we did in the class. Okay? So that cannot be a reason for not studying or not being up to date. Okay? The same goes for everyone. Yes, Ali Zulkarnain. चांद खुशी,
यस मैम।
बेटा क्या पढ़ा था हमने?
मैम हमने टाइम के बारे में पढ़ा था कि
क्या पढ़ा था?
वन रेवोल्यूशन, टाइम के बारे में, रेवोल्यूशन के
टाइम
बारे में पढ़ा था
पीरियड।
कि
टाइम पीरियड का सिंबल क्या होता है? व्हाट इज द सिंबल?
मैम टी।
कैपिटल टी। ठीक है, हाँ जी।
यस। और मैम हमने कोसाइन के बारे में पढ़ा था
डिफाइन
कि
करो टाइम पीरियड क्या होता है? टाइम पीरियड, व्हाट इज टाइम पीरियड?
मैम टाइम टेकन टू कंप्लीट वन रेवोल्यूशन।
One complete revolution, very good. And if we are talking in terms of sinusoidal waves, then the time period is defined as one crest plus one trough. This is one time period, okay?
यस मैम।
ठीक है, अच्छा जी, yes. And what are the
Ma'am,
units?
values of cosine.
एक
मैम
मिनट, अच्छा,
कोसाइन।
एक मिनट। अच्छा चलो ठीक है, चांद, लेट्स सी व्हाट दिस गर्ल इज सेइंग. क्या नाम था अभी, कौन बोला था?
Myself.
जी माइजा, व्हाट वर यू सेइंग?
Ma'am, values of cosine पढ़ी थी.
कोसाइन, हाँ
Values of cosine.
हाँ बेटा, क्या? कोसाइन, ठीक है. दिस हमने जो इक्वेशन लिखी थी ऑफ ऑसिलेटरी मोशन, वी यूज्ड अ कोसाइन फंक्शन एंड वी आल्सो टॉक्ड अबाउट द कोसाइन फंक्शन. साइनोसॉइडल वेव्स इंक्लूड साइन एंड कोसाइन फंक्शंस, ठीक है. तो प्लस माइनस 1 वाज द मैक्सिमम वैल्यू जो यहाँ पे फॉर एग्जांपल आती है, ठीक है. और इसके, वेरी गुड. और who would like to contribute? बेटा आप लोगों को पढ़ना चाहिए so that you can prepare for the homework जो मैंने आजकल में अपलोड कर देना है. और उसके अलावा of course for your final exam and also prepare your lab work. Yes, मुआज,
यस मैम।
बेटा क्या पढ़ा था हमने?
मैं लास्ट क्लास में था नहीं, मिस हो गई और आपके ऑनलाइन
Again, the
लेक्चर अटेंड नहीं
answer
किया
is
तब
the
तक।
same like I just said before. That's not a reason for not knowing what we studied. All information is available. ठीक है. अच्छा जी, फरीद.
I was at a funeral of my grandfather
Oh,
on
yes,
Monday,
I'm so
so I
sorry.
didn't see.
Yes, I heard about it. So,
मैम आपने लास्ट लेक्चर अपलोड तो नहीं किया हुआ, अब मैं उसको कैसे स्टडी कर सकूं जब वो अपलोड ही नहीं हुआ यूट्यूब पे?
मैं पता चेक करती हूँ कौन कौन सा आपने स्टडी किया हुआ है, ठीक है. आई नो आपने
आपका
कौन सा वाला स्टडी किया है, ठीक है. अच्छा, लेट्स गो नाउ टूवर्ड्स द बुक. आई एम गोइंग टू शेयर दिस विद यू. So you can see the book, right?
Yes.
So this was the definition that we were talking about. These were the formulas, the concepts, and the equations that we studied for the last class. And you can see in this case, we talked about time period. The formula for time period was the inverse of frequency. And we also talked about frequency. And this is the cosine function we were talking about. The equation of oscillatory motion, in fact, scientifically in this case, is particularly known as simple harmonic motion. And this is the equation that represents simple harmonic motion. What is X? X is yes, X is yes, Hamza Dar. Yes, Hamza Dar.
Ma'am, amplitude.
X is displacement, ठीक है. The maximum displacement is not known as amplitude, and that is represented by xm. M for maximum. So x is displacement, xm is maximum displacement, which is known as amplitude, right? And similarly, we talked about the terms omega and phi, and this is the formula. This is similar to the formula that we studied when we were studying circular or angular motion. Again, you can see the velocity and the acceleration. Okay, so we studied these concepts last time. We also talked about the mass spring system and hence the Hooke's law and the formulas related to that. Okay, so we continue from there. Yeah, यहाँ तक पढ़ा था हमने the mass spring system. Okay, now the energy in simple harmonic motion. You know that in mechanics, whenever a body is moving, it has a certain energy which is known as the kinetic energy, and also energy associated with its position is known as potential energy, which we are representing by U. So in this case, since the motion is represented by a cosine function, so we can define the potential energy in terms of this cosine function. So half kx squared, since we are talking of a mass spring system, which is also called a linear oscillator. So it is when you stretch the spring or you compress the spring, it starts oscillating. And therefore the corresponding potential energy is given by this equation. Now you can see that these diagrams represent the motion in terms of the sinusoidal waves that we were talking about. If we plot it graphically, we will see that these are the kinds of waves that we see. So kinetic energy in this case is represented by K, and you have T in brackets, which means that it depends upon time. The standard formula, as we know, is half mv squared, and then we substitute the value of V with the equation that we studied last time for this motion. So again, the same law that we've been studying throughout the book, which is the total energy is equal to the sum of the potential energy and the kinetic energy. And potential energy U plus kinetic energy K, and if you substitute their values, you get the combined formula. And this formula again can be simplified, you know, cos squared theta plus sine squared theta is equal to 1. So therefore it simplifies, and this is the final equation that you get. Now, if you plot this as a graph, you take T, the time, along x-axis, you take energy E along the y-axis, and you see that this green line represents the potential energy. The red line is the plot of the kinetic energy. At any one time, you will see that the sum of the potential energy and the kinetic energy is the same. But you can see that when the potential energy is maximum, the kinetic energy is minimum. And when the kinetic energy is maximum, the potential energy is minimum. And in between, they still, their values vary in such a way that the total energy of the system is conserved. This is another graph that represents this energy versus displacement. The difference between the above graph and this lower graph is here you have time along x-axis and here you have displacement along x-axis. So this is what the graph looks like when you plot it versus displacement. So this is the maximum amplitude on one side and the minimum amplitude on, this is the rest position, the equilibrium position, and this is the amplitude on the other side towards the negative. And this is the total energy which remains U plus K. Again, this system is, as I said, is similar to the mass spring system. And in the mass spring system, we have the concepts of inertia and we have the concepts of springiness. So the potential energy and kinetic energy depend upon these concepts. This is an example of, you know, when we talked about pendulum, we talked about the to and fro motion, a linear oscillator. This is an angular harmonic oscillator, in which case it's a twisting of a rotational motion, right? And the corresponding equation, then whenever there's a rotational motion, there's a torque and there's a moment of inertia instead of mass. Now the simple pendulum that you're all familiar with, as we also mentioned in the beginning of the chapter, you just have a simple thread and you have a small ball, a small mass attached to this. The length of the thread is L. And the mass of this bob is M. So if we draw the force diagram that we've been drawing from the beginning of the chapter, what are the forces that act upon this mass? Of course, the mass is being acted upon by the gravitational force, which is vertically downwards. We also know that when we pull something with a string, there's a tension in the string, and this force is acting in the upwards direction. But then we know that in order to balance these forces, we split them into rectangular components. So the the force that will be pulling the mass towards the mean position will be Fg sine theta, and the force that will balance the tension will be Fg cos theta. S is the arc length, because if you reproduce this path, this is like the radius in circular motion. So S is equal to the radius multiplied by the angular displacement, which is theta. So the formula for torque, as we remember, is the moment arm multiplied by force. The moment arm in this case is L, and the force that is pulling this towards the mean position is Fg sine theta. So you can have it like this. And also we know that this torque depends in angular motion on moment of inertia multiplied by the angular acceleration. So these two equations are equivalent, and we can write them like this. And finally, we can find the value of angular acceleration, which is alpha. And now, using the same concepts as before, we can find the value for the time period of a simple pendulum. And this is an equation, a very simple equation that you must have studied in O levels or in FSC, whatever. In that case, you know that the time period depends upon the length L of the amplitude, which we just discussed. It's proportional to the square root of the length L. The rest are constants. So this is called a simple pendulum, right? But now in reality, other bodies can also behave as a pendulum, and they are known as a physical pendulum. So a simple pendulum is the standard case that we do in the lab to understand the concept. Just a string and a mass, it simplifies the problem. But if you have, for example, a body which is shaped like this, let's say like a baseball bat. Now in this case, it will be slightly different, because in this case, the mass is not concentrated at one point, rather it's distributed along the structure of this pendulum. And if we apply the concept of moment of inertia, then we can, instead of the equation above, this equation gets modified in terms of the moment of inertia. Okay, well, I will come to these problems, and before that, I would like to talk about circular motion and how this is also a kind of simple harmonic motion, right? So simple harmonic motion and circular motion are equivalent, and they can be described with the same concepts. We have studied angular motion or circular motion before as well. So this is motion again along a circular path. So in this case, you can see that the body, let us say P, is moving from a certain distance, let's say X, from a point O, and it will cover a circular path. So whenever this body is covering a circular path, let's say it moves from a point P to a point P prime, then we can drop a perpendicular from there and plot its position. If we go on plotting its position, we will see that all the dots will be like this. You know, they will go towards the mean position on the positive side, and then on the negative side they will go reach a maximum amplitude. The maximum amplitude in this case will be equal to the radius of this circle, which is xm. And so this will be an example of a to and fro motion. And this concept was studied for the first time by Galileo Galilei. I'm sure you're familiar with him. He's a very famous Italian scientist. He's also known as the father of modern science. So he was using his telescope to observe the motion of planets, right? And the moons of Jupiter's, right? So he saw that when you, for example, put your telescope at one side and the moon is actually moving in a circular path, but when you observe it, you will see it oscillating to and fro from a certain mean position. And that's how we understand that this is also an example. Circular motion is also a case of simple harmonic motion. So simple harmonic motion is the projection of uniform circular motion on a diameter of the circle in which the circular motion occurs. So we can again we have already studied these concepts. In this case, the displacement is represented by an angle. And in some diagrams, we used theta. At this time, we're using omega t plus phi, using the equation that we use to describe the simple harmonic motion. Omega in this case is the angular velocity, right? Phi is the phase constant, and together this is known as the phase. And the linear velocity v, of course, we know can be related to the angular velocity omega. So this was the equation of motion that we did, right, as a cosine function. And then in terms of this, if you differentiate this, you get the velocity. And if you differentiate the velocity, you get the acceleration. Okay, so this was all about simple harmonic motion, and then circular motion as an example, as a case of simple harmonic motion. Another case we study is damped simple harmonic motion. So you are familiar with the concept of damping, right? So damping means that an external force, when acted on a body that is performing simple harmonic motion, will affect the motion of that body, right, of the oscillator, right? In this case, for example, you have a mass and a spring system. It is oscillating up and down, just like we studied before. In the previous diagram, we were studying the spring horizontally placed with a block. In this case, we have placed the spring and the mass in a vertical position, and it's oscillating up and down. The spring constant, which is also known as the springiness, is K. The mass of this block is M, and it's moving up and down. What's the difference in this case? The difference is that there's a rod attached, which in this case is being called the vane, and this is being dipped into water. So we have a beaker of water here, and whenever this body oscillates up and down, this rod dips into the water. But the effect of this is that it reduces this motion of the mass spring system, which is a harmonic oscillator. So it damps the motion. This concept is known as damping. It's represented by B. So when the motion of an oscillator is reduced by an external force, the oscillator and its motion are said to be damped. And this force, this external force that is causing this damping, is called Fd. And this depends on the velocity of this body. So therefore, using these concepts, we can write the equation for the damping force in terms of the damping constant. We can describe this motion again using the Hooke's law and Newton's second law. And we can find the equation for this motion, which will be slightly modified because we have included a term which depends upon the damping factor. And with the help of this, we see that the velocity has changed, and the new value of the velocity now includes this damping constant. So you see, what is the effect of damping? The effect of damping here can be seen in the form of again plotting this wave, and you see that what is changing in this wave. This is the amplitude xm plus xm and minus xm, but as the damping continues, this amplitude decreases and it will eventually cause the motion to stop. So that's the effect of the damping. So damping, kahan pe use hoti hai damping, for example? It has very practical uses, right? Can you think of an example of damping? Think about it.
Shock absorbers. Ma'am, it is used as a shock absorber.
Yes, very good. Yes, when of course, you want to decrease any damage due to the vibrations that are caused due to unwanted vibrations in a body, like a car in motion, for example. So in that case, you will see that you can use this concept to decrease those vibrations and control those oscillations, right? Okay, and every body, in fact, anything, for example, even if you're playing music, for example, a string of a guitar, for example, if you touch it and you leave it, you will see that it will vibrate, but then gradually the amplitude of vibration will decrease, and therefore you will see that the sound also decreases. In a car, shock absorbers are a good example of damped oscillations or a damped system, right? Okay. So let's look at this example problem, right? In this case, you have a damped oscillator, just the one that we've seen before, figure 15.15. This is 15.15, the same. And in this case, the mass of this oscillator is 250 grams. Again, notice that grams is not an SI unit. So when you're using it, you should keep that in mind. The spring constant K is given and the damping value is also given. Okay. So you can see that we have to find the period of motion, which is capital T. The formula for capital T that we just studied was 2 pi m over K. So applying for this formula, we can find the value of capital T. This is very simple. It's very straightforward. The only thing we've done is we've converted the mass from grams to kg. The rest of the values, we had them and we plugged them in and we got the answer. The second part is how long does it take for the amplitude of the damped oscillations to drop to half its initial value. It means that the maximum value was plus xm or minus xm plus minus xm, right? And now you have to reduce to xm over 2 to half. Okay? So this is how you represent it from the equation above that we have. So at t is equal to 0, the amplitude was xm, and later on this amplitude becomes xm over 2 or half xmn. So when you can cancel these terms from both sides and you can rewrite these terms in terms of this equation. I think you're all familiar with E. What is E? E sab jante hai na? You are all familiar with E.
Yes, ma'am.
जानते हो ना, in school in mathematics you've been studying E. E is a constant, ठीक है ना? It's a number. It's also known as a natural number or Euler's number, right? And what is Ln? Ln means
Natural log.
it is natural logarithm. So Ln is natural logarithm, E is an exponential term, and when you take Ln E, right, E raised to minus something, then the formula for this becomes log E is equal to 1. So you only get this term. ये याद है ना सबको? ठीक है? So in this case, for example, we know that log E itself will be equal to 1, and therefore you're only left with this term. And log E raised to any constant, let's say A, is equal to A multiplied by log E, which is equal to 1. And this is equal to 1 and this is equal to A, and we're left with just A. So using this, we get this value. ठीक है? We get just the exponential. And यहाँ पे when we get this exponential, we have we can substitute these values. Again, the values are already given and we can find the time for which xm will be equal to xm over 2. So, and the C part is how long does it take for the mechanical energy to drop to 1/2 of its initial value. Now, again, using the formula for mechanical energy that we have in the beginning, it was like this. Later on, this is what you get. And you have to now substitute the values and you can find the time. So now I'm going to take the attendance. Okay, so Sarmad, Amar, Abu Bakr, Fatima Babar, Khan Bajwa, Basharat Anam.
Present.
Okay, Bilal Muhammad, Hamza Dar,
Yes, ma'am.
Fariduddin,
Yes, ma'am.
Kessler, Zarish, Haris,
Present, ma'am.
Muaz,
Present, ma'am.
Muaz, yes, Ibrahim, Huma, Alina, Hunain, Rana Shehbaz,
Present, ma'am.
okay, Sania. Sania आई थी, फिर पता नहीं, I don't know if she disconnected after that. Okay. Arisha? Chand?
Present, ma'am. Risha, present.
Okay, Chand?
Present, ma'am.
Okay, Maiza?
Present, ma'am.
Yusuf Patras? Abira?
Present, ma'am.
Nadia? Hayan? Cheryl? Ashreb? Huda Zahoor? Amelia? Bisma? Sadiqullah? Sohaib? Talha?
Ma'am, so a present.
Okay. Zulkarnain? Ali Zulkarnain? Ali Zulkarnain log in करके गायब हुआ हुआ है. I can see him logged in, but he's not there. Okay. Right. So let's go back to the book again. So this was a problem on damped oscillations. After this, we have the concept of resonance. I'm sure you're familiar with the concept of resonance. So what is resonance? Anyone who can just give us an example or just a little short definition?
Ma'am.
Yes.
Okay, so resonance is when the oscillations or the vibrations of particles in one body match the vibrations and or oscillations of the particles in another body. They match it exactly. That phenomena is called resonance.
Very good. That's great. So Arisha, that was good. पहले किसने शुरू में आंसर किया था? अच्छा, so
शुरू में मैम जब क्लास शुरू हुई थी तब
हाँ जी, चांद ने
तब
किया
मैंने
था
किया था।
और एक लड़की भी थी, वो कौन थी?
मैंने माइसा.
फाइजा ने. अच्छा ठीक है. Okay, Maiza and Chand. Okay, right. Okay, so again, example of resonance. Who would like to give an example of resonance? अब definition तो हमने देख ली है. What's an example? Yes, Arisha.
The example of resonance is when during, for example,
एक
in
मिनट
earthquakes.
Arisha, let's talk to Abira. उसको भी point मिल जाए, ठीक है? आपको मिल गया.
Okay.
Abira, yes, do you want to answer this?
Yes, ma'am.
Yes, बोलो.
Yes, ma'am. Ma'am, for example, sometimes when you're playing a guitar,
Okay.
you just the guitar produces sound by vibrations. So when you pluck the string, it vibrates and transmits the energy into the
बेटा ये
body
नहीं
of the
पूछा था.
guitar.
Abira, no, that was not the question. Please address the question. Who would answer the question? An example of resonance.
As resonance, it means high amplitude. So we can say the amplification of guitar, or when a singer breaks the glass with his voice, he is increasing his
Okay.
voice at high amplitude.
Okay, yes. Okay, so that's an example. Another very simple example is also a child on a swing. All of us at some point in our lives, I'm sure, have sat on the swing. But you must have noticed that some children are really very good at swinging. Why are they good? What's the technique that they master? It's that, you know, when this swing is swinging back and forth, when the child reaches the maximum amplitude, it gives a certain push, and this then starts going further and further, and the amplitude increases. But then the example of the breaking of the glass by a musician is again a very good example. It has also, but it's not easy to happen. You can also see when the frequencies match, when two bodies oscillate with the same frequency, when the frequency of oscillation matches the natural frequency, the amplitude increases. And this can be used positively, and sometimes it can be very destructive as well. So for example, you can see in the case of an earthquake, for example, a building, if its frequency of vibration matches, it can cause a lot of damage, it can cause a lot of destruction, and maybe also loss of lives. So these are examples of resonance. You know, a very typical example is also, for example, if soldiers are passing from a bridge, they're told not to march on the bridge, because when you're marching, you're all going with a certain frequency, you're putting your steps in a certain frequency, and if that frequency happens to match with the frequency of the bridge, the oscillations will become the amplitude will become too large, and the bridge can even collapse. So these are all examples. So natural frequency of vibration is omega, and if this is matched with an external driving force, then we will have the phenomena of resonance. So in this case, omega d is the driving force frequency, and this is the natural frequency, and when they match, you have the displacement that changes. So this is again, and it gives you an increase, and therefore you get a peak in that case. So this is an example of an earthquake that happened, and in which buildings collapsed because of this phenomena. So we have now completed this. Your homework is to prepare chapter numbers 13 and 15 for the upcoming homework 4. Also remember to do your lab homeworks, just as you do every week. Okay? Right? ठीक है? So this is a summary.
Excuse me, ma'am.
जी बेटा, कौन बोल रहा है?
Ma'am, Rana Shahbaz. Ma'am, when you are going to open the homework?
I will tomorrow.
Ma'am, like time, ma'am, and it will be open for just for the one day?
I will notify you for how long I open it. Okay, but your task right now is to prepare it. ठीक है?
All right, ma'am. Thank you.
Okay. Take care. Bye bye.
Bye, man.
Goodbye, ma'am.
Take care.